Slides.
Thank you.
Connor is a fifth-year student at Duke and another one of our recently awarded neutrino fellows, and he's going to give us an overview of neutrino directional detection.
All right, thank you, and thank you for the invitation to speak today. I appreciate the
Connor,
work that's gone into putting.
We're seeing your presenter view on the screen share. Can you click the swap displays option in PowerPoint?
Yes. So that's still, let's see, swap displays. There we go. Okay.
Perfect.
Sorry about that.
Go ahead.
Thank you for the invitation to speak today. I appreciate all the work that's gone into organizing this. And I'd like to talk to you all about neutrino directional detection. And I want to emphasize out of the gate that I am by no means the first person to talk about a lot of these ideas. There was a great paper by Patrick Huber and Maitland Bowen, if I'm remembering right, just recently that covered a lot of what I'm going to talk about. And that was very good. But what I hope to convince you of is that our group at TUNL is uniquely well suited to realize some of the potentials of this technology. So to start out, neutrinos are a uniquely interesting tool for nonproliferation and nuclear reactor monitoring efforts because they can't be contained or blocked in any way if you have a hostile nation who is attempting to divert fuel or conduct any covert nuclear activity. They can keep you from seeing their gamma rays, they can keep you from seeing their neutrons, they can't block the neutrinos. Unfortunately, they are difficult to detect for the same reasons that they're impossible to contain. Existing detector technologies tend to be massive. We're talking kiloton scale detectors, and they generally are immobile. They have to be close to a reactor or else they get swamped by cosmogenic neutrino backgrounds, and they exploit a couple channels of neutrino interactions that have strong signatures like inverse beta decay or neutrino electron scattering, but not the maximum possible cross-section. One way to get around these problems is to think about a directionally sensitive neutrino detector, particularly a directionally sensitive sevens detector. The directionality buys you distance, basically. If you can isolate neutrinos coming from a particular source, you can move farther from that source and still not get swamped by cosmogenic backgrounds. And sevens buys you an increase in cross-section. Tyler already covered a little bit of the physics of sevens, but just to repeat, this is a standard model process predicted in 1974 by Daniel Friedman. It is so difficult to detect, we only first saw it in 2017, because the energies involved are very low by necessity. For it to be a coherent scattering event, you have to have less than 50 keV transferred from the neutrino to a nucleus. And additionally, that energy is quenched by something called the nuclear quenching factor, which I'll talk more about later. Cross-section is proportional to the number of neutrons squared, and it is a sort of uniquely sensitive process if you want to search for physics beyond the standard model for a lot of reasons that I'm not especially qualified to talk about, but so it's out there. There are many, many experiments all around the world currently in the hunt for sevens. Thus far, the COHERENT experiment, of which Tyler and I are members, is the only one to have successfully measured the process, but there are many more that are turning on in the coming years or that are currently collecting data, and we expect to have results soon. This map just highlights the international scope of the field. It has really emerged all over the world where there are reactors. And the timetable here just shows that we are entering a really intense period of activity for this new field. We're in 2020 now. There are a wave of detectors that are turning on in the next 2 years, all hoping to study this process and hopefully find some interesting new physics with it. I mentioned that Tyler and I are members of the Coherent collaboration, just to introduce that to those of you who might not know. The Coherent collaboration is a group of 22 institutions who got together with the explicit goal of measuring sevens in an array of detectors. We reported our first successful measurement with a cesium iodide sodium doped crystal in 2017. That result made the cover of Science. And our second measurement using a liquid argon detector was just recently reported. That's still in the publication process. We're going back and forth with reviewers now. There we go. To show you that liquid argon result for posterity, on the left here we have a cross-section versus energy plot. The two data points in green are the results of two independent analyses conducted within the collaboration. The Moscow analysis is in dark green. The US analysis is in light green. We see that they broadly agree with each other and agree with the predicted value from the fluxed averaged prediction in purple. On the right, we have what we call the n squared curve. This shows the sevens cross section versus the number of neutrons as you step through the elements. The black data points are nuclei that are included in coherent detectors, and the two blue data points here are now nuclei that we have actually measured. I want to pivot a little bit now and talk about what my specific contribution to the Coherent collaboration is. That is working on quenching factor measurements at the Triangle University's Nuclear Laboratory, or TUNL. The quenching factor is a way to describe this effect where electron recoils are easier to detect than nuclear recoils because the light yield or the charge yield or whatever your signal is tends to be higher for electronic recoils than for nuclear recoils, even at the same energy. The reasons for that are complex. It's all a big condensed matter problem. We don't get into that too much. What we focus on is measuring it. And we do that by scattering monoenergetic neutrons into known angles. So if you can create a beam of monoenergetic neutrons and stick a detector you're interested in into that beam, you can then array backing detectors at known angles relative to the beam, and the angle that a neutron scatters off of your detector into a backing detector through defines the KeV-NR, the nuclear recoil energy that neutron left in your detector, and then you can measure the electron equivalent energy, and the ratio of those two gives you your quenching factor. We have been doing these measurements for years now. We work with a broad group of collaborators from dark matter and neutrinos and nuclear engineering on a bunch of these measurements, and I'll highlight some of those for you now. One of our more recent results was a measurement of liquid xenon with a group from Lawrence Livermore National Lab and the LUX-LZ collaboration. They made a custom TPC for the liquid xenon that they brought out to TUNL. This nice picture here on the left is from Brian Leonardo. He was the postdoc in that, or excuse me, the graduate student in that group at the time. He has since moved on to a postdoc position. And the sort of significance of this result was that we saw a pretty significant divergence from the NEST model, which has been used to justify a lot of dark matter experiments for the last 10 years or so. I guess that difference will be important moving forward with WIMP searches and things like that. Oh, wrong way. Another recent measurement campaign we did was with the NewsG collaboration, another dark matter experiment. We looked at a mixture of neon and methane in what they call their gas ball detector. So this is a sphere of metal containing some gaseous target with a metal probe in the middle that's under high voltage to read out signals. And these results haven't been published yet, but I wanted to highlight them because it demonstrates that we've been able to do these types of measurements in a gaseous medium before, and I'll explain a little bit why that's significant later. This is a fairly comprehensive, not totally comprehensive, list of similar measurements we've done. We did cesium iodide for the coherent collaboration that ultimately got folded into the science paper. We looked at channeling in silbene with Robert Weldon and John Mattingly out of NC State University. We've looked at germanium for the coherent collaboration, sodium iodide for the coherent collaboration. We wrapped up a measurement campaign with the microchandler detector in the fall. A lot of my quarantine time has been spent on meeting with them to finish up the analysis of that data and write a paper, so that publication should be out soon. There was a helium-3 measurement. The analysis there is ongoing. Super CDMS came by, that's ongoing. And a paper I wrote early in my graduate career looking at EJ301 liquid scintillator. That was also used for the coherent experiment. We have a couple of background detectors that use EJ301 cells. Now, I talked about this potential measurements at the MTV meeting in March. Unfortunately, this had to be delayed, but we plan still at some point in the future to work with Sven Vossen from the CYGNUS collaboration to look at nuclear recoils in a gaseous TPC. So when I mentioned earlier that we had been able to see these recoils in gas before, that was in anticipation of this measurement campaign. They're hoping to bring a prototype TPC to TUNL to calibrate whenever restrictions at Duke lift. When that will happen is still unclear. And then ultimately they would like to build a larger scale version of their TPC to look at directional sevens detection. And we are sort of uniquely positioned to help them with that as members of the only collaboration to have measured sevens before, and as a group who regularly studies nuclear quenching factors. We're very much looking forward to getting this measurement done. Just briefly, I think I have maybe 30 seconds left. The other neutrino directional detection channels you can think about looking at include inverse beta decay. I've spent a fair bit of time thinking about this. With inverse beta decay, you have an anti-neutrino producing a positron and a neutron when it interacts with a proton. So if you have IBD on a hydrogen target, you can have a two-body problem. If you can image the neutron and the positron, you can reconstruct the track of a neutrino and point back to its source. How you do that is still an open question. We've looked at several designs. The easy answer is with a time projection chamber filled with some sort of hydrocarbon. Certainly, we're still very interested in that possibility and working towards realizing that. We've also come up with some other plastic scintillator panel detector ideas that I'm happy to talk more about with anyone who's interested. But with that, I will thank you once again for inviting me, and I'll take any questions.
Thanks, Connor. Very nice presentation. We have about 5 minutes for questions, so please speak up if you have a question for Connor. Okay, I'll take the session chair's privilege, I guess. I had a question about the quenching factor experiments you discussed at TUNL. I noticed in the citation there on the slide, you talk about measuring these functions for down to below 100 keV. That's a very challenging energy range for organic scintillators due to gamma interference. So can you talk a little bit about that experiment? Was it just time of flight that you used to get rid of the gammas, or was gamma interference a challenge for those experiments?
Let me find the particular slide you're talking about so that I know which citation you mean. This one?
Yeah. Nope, above. The one with this, there was a up. Up. This one.
This one. Yes, so we do obviously have gamma backgrounds. We have a pulsed beam that has pretty narrow timing structure, so that cuts down our backgrounds to a significant degree, and we do also put in a time of flight cut. So we have what we call the BPM, the beam pulse monitor, which is an inductive signal that passes out of the beamline to our digitizer and lets us know when a bundle of protons is making its way to the target. We then see a flash of interactions in the central detector that we're characterizing, and then sometime after that, those particles arrive in the backing detectors that are set back at a known angle. Between the timing cuts we can apply on BPM and on the time from the scatterer to the backing detector, we reduce our backgrounds dramatically. Rarely an issue.
That makes sense. Thank you. Other questions, please? Well, at the end, you mentioned a possibility of a plastic slab to detect directionality with IBD. Can you talk a little bit about that?
Sure. So this idea was born out of a desire for something a little easier to build than a time projection chamber. We were trying to think if there was something we could put together in the order of weeks rather than the months or years it would take to build a working TPC. The idea here is that you look for inverse beta decay in these slabs of plastic scintillator. Each slab has 4 PMTs located on each corner that help you triangulate the positions of interactions within the slab. And they're coated with lithium-6 or some other neutron capturing isotope. So you would see a flash from an inverse beta decay. And what you would look for would be, and this diagram isn't actually great. Our thinking on the process has evolved since I made this, but you would look for a neutron reaching an adjacent panel that is off to one side of the panel that the inverse beta decay happened in and capturing. And then you would look for the positron going the other way and leaving you a long track of flashes through these panels as it moves. So you would only be getting a subset of IBD interactions where the neutron and the positron are more or less back to back. So you lose some signal rate there, but you control the density because you control the panel spacing. One of the things we've realized is important in all of our detector design efforts is the exact balance of the density you achieve. Neutrons and positrons behave so differently as they move through your detector that building one detector to encompass both of them is tricky if you can't control your density. The other advantage this design has is that it's very simple. You can knock this out in no time. And if a component of it breaks, it's a fast repair as well. So you lose a lot of signal, probably close to 90% of IBD events will not meet the selection criteria for this sort of detector, but those 10% are really, really easy to measure.
Can you give me a sense of scale on this diagram? Like how big are we talking here?
The prototype we've built in the lab, which I should stress we have not turned on or looked for neutrinos with yet, is 30 by 30 centimeter panels that are half a centimeter thick, and we're thinking about spacing them probably 30 centimeters apart. And you can sort of scale that arbitrarily depending on the rate you're looking for.
Great, thank you. Thanks, Connor. That's our time. Really appreciate your presentation.